Here's another video where we practice with predicate logic proofs. This video will focus on the use of universal introduction and existential elimination. Again, the focus is not on explaining these rules in general or giving their presentation. For that, you'll have to look at earlier videos I've done, and I'll put links in the description below. One thing to note is that I encourage you to pause the video now, try these proofs yourself, and then watch the video to kind of get confirmation as to whether or not you did the proof correctly. One thing I'll also do is put timestamps to each one of these proofs in the description below. That way, if proof 1, 2, or 3 is pretty straightforward, but you have difficulty with 4 and 5, you can skip directly to proof 4 or 5 by clicking the links in the timestamps. In this proof, I want to reason from everyone is a person, or AXPX, to everyone is a person or a queen. And so I'm reasoning from a universally quantified expression to another universally quantified expression. I'll start by setting up the proof. I'll simply write AXPX. And my goal will be to derive this universally quantified expression over there. The first step is to make use of universal elimination, replacing every universally quantified variable with any name of your choosing, but the replacement must be uniform. So I'll use one universal elimination here. Now, since I see my conclusion has this disjunction in it, I'll make use of the disjunction introduction rule, which says that if you have a formula, then you can reason to a disjunction where the formula that you're reasoning from is one of the disjuncts. So this is by line 2, disjunction introduction. Now that I have this disjunction PA or QA, I can use the universal introduction rule, which says that I can replace each one of these names A with a universally quantified variable, provided certain conditions are met. And those conditions are things like that the name is not found in an assumption of an open subproof, and A is not found as one of the premises. And so since this formula meets these restrictions, that it doesn't violate any of those restrictions, I can use the universal introduction rule on it. And so this is AX, PX, or QX. And this is by 3 universal introduction. There's a couple things about this particular proof I want to note in terms of some common problems I see people make. Sometimes people will try to reason directly from line 1 to the conclusion, AX, PX, or QX. And they'll try to do this using disjunction introduction. This is not an acceptable use of disjunction introduction. You could reason from line 1 to say a formula like AX, PX, or I don't know, QA, using disjunction introduction. But it's important to note that when you're using disjunction introduction, you're actually forming a disjunction. You're introducing into the proof a disjunction. Whereas this formula, this AX, PX, or QX, is not a disjunction. It is a universally quantified formula. In contrast, an acceptable use of disjunction introduction would be this AX, PX, or QA, because this formula, AX, PX, or QA, is a disjunction. In this proof, we'll reason from existentially quantified X, PX to existentially quantified X, PX, or HX. The idea here is we're reasoning from a sentence like someone is a person to someone is a person or a horse. We'll start by setting up the proof, and that involves simply writing the formula EX, PX, and indicating that this is a premise or a formula that is provided for us. So we have this EXPX, and there's no way to directly reason from EXPX to EXPX or HX. We'll have to make use of the rule existential elimination. And this rule starts with an assumption. We need to make an assumption that is based on the existing existentially quantified formula in the proof already. So what we're doing here is that if this says someone is a person, we're making an assumption that A this individual that's going to pick out, or this name that's going to pick out an individual that has this property. We're just assuming temporarily that this name is picking out the same object that EXPX is. There's an important thing to note though, that when we pick a name here, the name has to be completely foreign to the proof itself. So if you had PB or PC in the proof already, you'd want to make sure you pick a different name, not PB if B is already found, or not C if C is already found. So now that we have PA, which is assumed at line 2, we can use disjunction introduction to reason to PA or HA. So this is by 2 disjunction introduction. At line 4, we can now use existential introduction to form this EX, PX, or HX. So EX, PX, or HX by 3 existential introduction. The idea here is that since this A is a name, we want to make sure we remove that name from the proof. We don't want to reinsert it into the proof because we don't want it to convey that there is an individual who we know specifically that has this particular property. We're saying that someone has the property, not an individual that we're naming. In this assumption here, we're only using the name temporarily for the purpose of proof. We're not going to ultimately reason to a specific individual has the property of being a person or being a horse. So another way of putting it is that the formula, the name that you've assumed at line 2, needs to be removed before you derive a formula from that assumption or subproof. So now that we have this EX, PX, or HX at line 4, we can reason to EX, PX, or HX from the subproof and the existentially quantified expression at line 5. So we can reason to EX, PX, or HX. And this is derived from lines 2 through 4, as well as 1. 1 and then 2 through 4, and this is by existential elimination, this EE rule. So what we've done is we started with an existentially quantified expression. We then moved to a subproof that was based upon that existentially quantified expression. We reasoned to a formula that does not contain the name that was originally assumed, and given that it doesn't contain the name, we can reason to this particular formula directly from line 1 and the subproof. In the following proof, we'll reason from AX, PX, EX, QX to the expression EX, QX, and PX. We'll reason from, let's say, everyone is a person and someone is a queen to someone is both a queen and a person. We'll start by setting up the proof, which involves simply writing both of the formulas that are to the left of the syntactic turnstile. So this is AX, PX, as well as EX, QX. The next step will be to try to introduce into the proof this existentially quantified expression here. And while we might try to reason from line 1 to PA or PB, that won't give us this existentially quantified expression. We really need to leverage this existentially quantified expression at line 2. And so the way to start is by at line 3 making an assumption based upon line 2 for the purpose of using existential elimination. So line 3 involves an assumption where we simply replace the variable x with a, and it's acceptable to use this if we ultimately plan on using this subproof for existential elimination, because this a right here is not already found in the proof itself. So now what we can do is use line 1 to derive PA. And this is by 1 universal elimination. We're taking that x and replacing it with a. Now that we have PA, we at line 5 can take those two formulas and put them together. If QA is the case, then PA is, and PA is the case, then we can reason to the conjunction QA and PA. So this is by lines 3, 4, conjunction introduction. We're simply just taking lines 3 and 4 and forming a conjunction out of them. Now that we have QA and PA, we want to somehow pull this formula out of the subproof. We want to reason from the reasoning we've done in this subproof to the main line of the proof. but we can't simply reason directly to QA and PA. What we'll need to do is sort of clean QA and PA up by making sure that the formula that we're reasoning to doesn't contain the name that we've assumed at line 3. And so we'll make use of existential introduction here, replacing the A with X. So this will give us each of these A's with X. This will give us EX, QX, and PX. And this is by line 5, existential introduction. The thing to note that this is actually our conclusion here, so it's desirable to derive this formula. And we can at line 7 using existential elimination. In using existential elimination, we're reasoning from 2, which is the existentially quantified expression on which everything is built, and this entire subproof 3 through 6. So this is 2, 3 through 6 existential elimination. Existential elimination allows us to write this last formula outside of this subproof, given that we have a subproof that is based upon an existentially quantified expression at line 2, and we meet the restrictions associated with existential elimination, which is that this A is foreign to the proof itself, and the formula that we're reasoning to does not contain the name that we assumed at line 3, which is the assumption. In this fourth proof, I want to take a look at solving a proof with 0 premises, that is, just reasoning directly to a particular formula. A lot of times people have questions about how to do these particular proofs, particularly because people like to reason from premises to a conclusion, but when you don't have any premises here, it's unclear what to do. So what you'll need to do is to start the proof by making an assumption. And so we'll start this proof by simply assuming PA. The idea here is that ultimately we want to reason to the conditional PA then PA, and then we can make use of universal introduction to derive the universal quantified expression here. So by assuming PA at line 1, then we can reiterate PA at line 2. So this is by 1 reiteration. The idea here is if PA is the case, then PA is the case. And so we can rewrite this formula. At line 3 now, we can derive the conditional if PA then PA. So this is by the subproof 1 through 2 conditional introduction. The idea here is we're just rewriting the content that's found in the subproof. In the subproof we said assume PA is the case. Well, if PA is the case, then PA is the case. And so we're just deriving this conditional based upon this subproof. That's something we've proven in this other subproof here. But now that we have PA then PA at line 3, we can use universal introduction on this particular formula, PA then PA. We can replace each of the names with the universally quantified variable x. And so we'll replace this first A with x and the second A with x. This doesn't violate any of the restrictions because A is not found in an open subproof, A is not found in a premise, and so we can use universal introduction on it using from line 3 universal introduction. So we are able to derive this entire formula, AX, PX, then PX, simply from making an assumption, reasoning to this conditional, and then using universal introduction to complete the proof. In this last practice problem, what I want to derive is the existentially quantified expression EX, not PX, or PX. Again, this is a zero premise deduction or zero premise derivation, and so we'll have to start by making an assumption. My thought process in looking at this particular proof is to say, well, what I would ultimately like to derive is something like PA or not PA or PA. And then if I have this formula, I can use existential introduction on it to derive my conclusion. So in thinking about trying to derive this particular formula, that's how I'm going to base my initial assumption. And so I'll say, well, this is a disjunction. One way to try to derive this particular formula is to assume the opposite of what I want, and then use negation introduction or negation elimination, or sometimes called proof by contradiction, to derive this particular formula. So I will make the assumption not PA or PA. So here's my assumption, and my goal here will be to try to derive a contradiction. And looking at line 1, I'll use De Morgan's laws on this to derive not PA and not PA. So this is by line 1, De Morgan's laws. Then I'll break the conjunction apart, which will allow me to derive not PA and not PA. So this is by 2 conjunction elimination. So now that I have a formula and its literal negation, what do I have here? I've made this assumption, and I've shown that from this assumption it follows not PA and not PA. And so I can use the negation elimination rule from the subproof 1 through 4 to derive the formula not PA or PA. So I've shown that this particular assumption leads to what we'll call it absurdity, a formula and its literal negation, so the opposite must be the case. Now that I have not PA or PA, I can make use of existential introduction to complete the proof. I can replace each one of these A's with the existentially quantified variable. So I'll reason to EX, not, and here again I'm replacing the A with the existentially quantified variable, or PX. And this is by 5 existential introduction, because I'm introducing into the proof this existentially quantified expression.